In this lecture, we are going to discuss first, what is quality control? Second, phases of quality assurance. Third, inspection. Fourth, statistical process control. Fourth, control process. The purpose of quality control is to assure that processes are performing in an acceptable manner. Companies accomplish this by monitoring process output using statistical techniques. So, quality control is a process that measures output relative to a standard and takes corrective action when output doesn't meet standards. If the results are acceptable, no further action is required. At acceptable results, call for corrective action. Note that every process generates output that exhibits random variability. That is natural and cannot be corrected. However, if there are no random variations in process output that can be corrected, so quality control tools are used to decide when corrective action is needed. Quality assurance that relies primarily on inspection of lots or batches of previously produced items is referred to as acceptance sampling. Quality control efforts that occur during production are referred to as statistical process control. Also, the best companies emphasize designing quality into the process, thereby greatly reducing the need for inspection or control efforts. As you might expect, different business organizations are in different stages of this evolutionary process. Some rely heavily on inspection. However, inspection alone is generally not sufficient to achieve reasonable level of quality. Many occupy a middle ground that involves some inspection and a great deal of process control. The figure you see illustrates these phases of quality assurance. Inspection. Inspection is an appraisal activity that compares goods or services to a standard. Inspection is a vital but often unappreciated aspect of quality control. Although for well-designed processes, little inspection is necessary. Inspection cannot be completely eliminated. And with increased outsourcing of products and services, inspection has taken on a new level of significance. Note that in lean organizations, inspection is less of an issue than it is for other organizations, because lean organizations place extra emphasis on quality in the design of both products and processes. Moreover, in lean operations, workers have responsibility for quality, which means quality at the source. However, many organizations don't operate in a lean mood, so inspection is important for them. This is particularly true of service operations, where quality continues to be a challenge for management. Inspection can occur at 3 points: before production, during production, and after production. The logic of checking conformance before production is to make sure that inputs are acceptable. With the logic of checking conformance during production is to make sure that the conversion of inputs into outputs is proceeding in an acceptable manner. The logic of checking conformance of output is to make a final verification of conformance before passing goods on to customers. Inspection before and after production often involves acceptance sampling procedures and monitoring during the production process is referred to as process control. Also, to determine whether a process is functioning as intended or to verify that a batch or lot of raw materials or final products doesn't contain more than a specified percentage of defective goods, it's necessary to physically examine at least some of the items in question. The purpose of inspection is to provide information on the degree to which items conform to a standard. The basic issues are: first, how much to inspect and how often. Second, at what points in the process inspection should occur. Third, whether to inspect a centralized or on-site location. Fourth, whether to inspect attributes, in other words, count the number of times something occurs. Or variables, in other words, measure the value of characteristic. How much to inspect and how often? The amount of inspection can range from no inspection whatsoever to an inspection of each item numerous times. Low cost and high volume items such as paper clips, roofing nails, and wooden pencils often require little inspection because, first, the cost associated with passing defective items is quite low. And second, the processes that produce these items are usually highly reliable, so defects are rare. Conversely, high cost and low volume items that have large costs associated with passing defective products often require more intensive inspections. As illustrated in the figure, you see, if inspection activities increase, inspection costs increase, but the costs of undetected defects decrease. Note that the traditional goal was to minimize the sum of these two costs. In other words, it may not pay to attempt to catch every defect, particularly if the cost of inspection exceeds the penalties associated with letting some defects get through. Current thinking is that every reduction in defective output reduces costs, although not primarily by inspection. Where to inspect in the process. Many occasions have numerous possible inspection points. Because each inspection adds to the cost of the product or service, it's important to restrict inspection efforts to the points where they can do the most good. In manufacturing, some of the typical inspection points are: first, raw materials and purchased parts. There is little sense in paying for goods that don't meet quality standards and in expending time and effort on material that is bad to begin with. Supplier certification programs can reduce or eliminate the need for inspection. Second, finished products. Customer satisfaction and the firm's image are at stake here, and repairing or replacing products in the field is usually much more costly than doing it at the factory. Likewise, the seller is usually responsible for shipping costs or returns, and payments for goods or service may be held up pending delivery or satisfactory goods or remedial service. Well-designed processes, products and services, quality at the source, and process monitoring can reduce or eliminate the need for inspection. Third, before a costly operation, the point is to not waste costly labor or machine time on items that are already defective. Fourth, before an irreversible process. In many cases, items can be reworked up to a certain point. Beyond that point, they cannot. Fifth, before a covering process, painting, plating, and assemblies often mask defects. Centralized versus on-site inspection. Some situations require that inspections be performed on-site. For example, inspecting the hull of a ship for cracks requires inspectors to visit the ship. At other times, specialized tests can be best performed in a lab. For example, performing medical tests or analyzing food samples, or testing metals for hardness. Note that the central issue in the decision concerning on-site or lab inspection is whether the advantages of specialized lab tests are worth the time and interruption needed to obtain the results. Also note that reasons for favoring on-site inspection include quicker decisions and avoidance of introduction of extraneous factors. On the other hand, specialized equipment and a more favorable test environment offer strong arguments for using a lab. Statistical process control. Quality control is concerned with the quality of conformance of a process, which means does the output of a process conform to the intent of design, and variations in characteristics of process output provide the rationale for process control. Statistical process control, shortly SPC, is used to evaluate process output to decide if a process is in control or if corrective action is needed. Process variability. All processes generate output that exhibits some degree of variability. The issue is whether the output variations are within an acceptable range. The issue is addressed by answering two basic questions about the process variations. First one is, are the variations random? If non-random variations are present, the process is considered to be unstable, and corrective action will need to be taken to improve the process by eliminating the causes of non-randomness to achieve a stable process. The second one is, given a stable process, if the inherent variability of process output within range that conforms to performance criteria, and this involves assessment of a process's capability to meet standards. If a process is not capable, that situation will need to be addressed. Variation. The natural or inherent process variations in process output are referred to as a chance or random variations. Such variations are due to the combined influences of countless minor factors, each one so unimportant that even if it could be eliminated, the impact on process variations would be negligible. Note that in Deming's terms, this is referred to as common variability. The amount of inherent variability differs from process to process, of course. For example, older machines generally exhibit a higher degree of natural variability than newer machines, partly because of worn parts and partly because new machines may incorporate design improvements that lessen the variability in their output. A second kind of variability in process output is called assignable variation or non-random variation. Note that in Deming's terms, this is referred to as special variation. Unlike natural variation, the main sources of assignable variation can usually be identified. In other words, assigned to specific cause and eliminated, of course. Sampling and sampling distributions. In statistical process control, periodic samples of process output are taken, and sample statistics such as sample means or the number of occurrences of a certain type of outcome are determined. The sample statistics can be used to judge randomness of process variations. The sample statistics exhibit variation just as processes do. Note that the variability of sample statistics can be described by its sampling distribution, a theoretical distribution that describes the random variability of sample statistics. For a variety of reasons, the most frequently used distribution is the normal distribution. In the case of sample means, the central limit theorem states that as the sample size increases, the distribution of sample averages approaches a normal distribution regardless of the shape of the sampled population. This tends to be the case even for fairly small sample sizes. For other sample statistics, the normal distribution serves as a reasonable approximation to the shape of the actual sampling distribution. Sampling and corrective action are only a part of the control process, and the steps required for effective control are: 1. Define, which means what is to be controlled. 2. Measure, which means How will measurement be accomplished? 3. Compare, which means there must be a standard of comparison. 4. Evaluate, which means establish a definition of out of control. 5. Correct, which means uncover the cause of non-random variability and fix it. 6. Monitor, which means verify that the problem has been eliminated.